of them is just right out impossible, right? I mean, we looked at Fibonacci, right? The Fibonacci sequence you can write recursively really easily, but what happens when you try explicit? You don't know how to do that. Like, you flat out don't know how to do that yet. You could write down, like, I could show it to you and you could use it, like it uses mathematical operations you've seen before, but you wouldn't be able to construct it. But, so anyway, when it asks the formula, it's either one recursive or explicit, which is really nice.
If it's the first time I look at 1 and then 2, and then the second time 2 and then 5, and then see where 2 will be 5 and 1 will be 2.
Oh, interesting. I like that. That's cool. What was the formula for 3?
I said n squared.
Yeah, it's n squared plus 1, exactly. So I was just trying to get at, you should also keep in mind that squares or cubes can be in there. And you should just know your basics, cubes and squares. Okay. Notationally, when we're talking about sequences, I blinked this on the board a little bit last class, but S1, S2, why do we have the 1, 2, 3, and why are those there? Well, why don't we just say S1, 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 S1? So yeah, we need an index. No, it's a basic question, but you need an index. The order is important. If you change the order of a sequence, it becomes a different sequence. The order is important. Okay. The sequence has a limit L written. Can someone read that out loud to me? What does that say right there? Can someone just read this?
As limit n goes to infinity
Of
of Sn equals
L. If this is the sentence right here, that's killer. This is the part of the sentence I think that's killer. It is proper, but it's killer. If Sn is as close to L as we please whenever n is sufficiently large. Huh? Here's what that means. Here's what that means. Something is a limit if you can get arbitrarily close to it. What does arbitrary mean? What does arbitrary mean? Yeah, it's one definition for arbitrary, but you can get as close as you want. So, for example, let's say the operation was I go halfway the distance to the wall. If I go halfway to the wall, and 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 halfway to the wall. Let's say you said a foot. Let's say, Cece, you said an inch. Let's say you said a millimeter. Can I always get that close if I wanted to? Yes. By going halfway to the wall and halfway to the wall, I can get as close as I want to. There's no barrier except for the wall. Am I ever get against the wall? Technically not at finite time, right? But the idea is no matter what distance anybody specifies, can I get that close to the wall? Yes. Therefore, the wall is the limit of the operation halfway, 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 halfway. What it's saying is Sn can get as close as you want to L whenever S is sufficiently large, whenever n is sufficiently large. So in terms of what I was just showing you, n1 would be like going halfway once, n2 would be going halfway twice. So you can get as close as you want. If the limit L exists, we say the sequence converges. If no limit exists, it diverges. Yay! And you might have seen some ways in which things converge and they diverge. What's one way a sequence diverges? Yeah, oscillates. That's kind of the cool one. It goes back and forth, so it's definitely not going to anything. What's another way a sequence diverges? I'll give you a hint. It just goes. It just keeps on going up, like 2 to the n, like 2, 4, 8. It just exponential r ratio greater than 1. It keeps going. Right, exactly. It's like there's many different ways. So you might have seen this. This is key here. To calculate the limit of a sequence, we use what we know about limit functions, including the things in theorem 1.2 and the following facts. So here's the thing. You can be really sure of something. You can be really, really, really sure of something, but proving it true is totally different. Do you understand what I'm saying? And there are many things. This happens all the time in your math career. It's happened many times. You didn't know this, where you've been presented with something as true that you didn't know really does need a proof. Why don't they just show you the proof right then and there? Proofs can be hard and sometimes use math that you don't know yet. So there are lots of things in calculus, actually, a ton of things in A, B, and B, C multi that you don't prove and that you don't even know need to be proved because you can't prove them until you get to like junior year of college. There's a class called analysis, real analysis. Take it, it's fantastic. But they give you tools instead. They give you truths. They give you truths, which are really key. This sequence, Sn equals xn, converges if the absolute value of x is less than 1, and it diverges if the absolute value of x is greater than 1. Greater than 1. We're not proving it, they're just telling you that's true. Second thing, the sequence 1 over n to the p converges to 0 if p is greater than 0. So these are two truths that they're just giving you. So you can now use these truths. Do you remember doing proofs in geometry? Remember how you said like theorems, like if this is true, these are theorems that you can now use to prove other sequences converge or diverge. So let's take a look at A right here. What can you tell me about A? Do you think it converges or diverges? Yes, it does converge. Why?
Because the ratio is less than 1.
Yeah, 0.8 is less than 1, so therefore it converges. Is that good? It's exciting? Okay. What about this one? Does B necessarily fit directly into either one of those truths right above? I mean, when you look at it, does it just automatically identify? Not really, right? So if it doesn't look like what you want, are there some simple things we can do to make it look a little cleaner? I don't like negative exponents. No, can't quite flip it. Close though. What's this going to be? 1 minus what? 1 over e to the n. And what's the bottom one? E to the n. Okay, nice. We have not changed any values. All we have done is rewritten. Correct? That's all we've done. Nice. Okay, when it says does it converge or diverge, we're looking at the limit, right? This is the, what does this sequence do? What do we know from, oh, look at this. The sequence Sn 1 over n converges to 0 if p is greater than 0. What's going to happen here? We know e, that's a number, right? 2.7, blah, blah, blah. As this gets huge, this infinity going to be greater than 0. Look what it says here. P is greater than 0. Where's p? The power, right? So what do we know about this and this? What are they both going to do? They're going to get smaller and smaller and smaller and smaller and smaller. What do they converge to? 0. So you know that this and this, what do they both do? They go to 0. So what does Sn, what does it go to? 1. So the limit of sorry, I'll write this properly. The limit as n goes to infinity of Sn, what's that going to go to? 1. That's correct. Let's look at the next one. This is fun. Remember when you're doing limits, you can always try to just plug numbers in or make a table. In this case, when you're looking at that, you might not quite be sure what's going on, but then if you start writing out the terms, so it's n, I think n starts, what do we say here? N's going to start at 0 on this one. Let's say n starts at 0, greater than or equal to 0. So what happens to that? When n is 0, what does this equal? What's the first term? 2. And then what's the second term? 0. And then what is it? 2. And then what is it? 0. So what's going on here? It is divergent or convergent. It oscillates, but it not only does it oscillate, it does not converge. There are oscillating functions that actually converge. Like you can go up and down and get smaller, right? So that oscillates technically. This one oscillates, but does it ever converge? No. So this diverges. Is there any number that this gets arbitrarily close to? No. No, there is no number that it gets arbitrarily close to. So okay, so then you get more fun, dense statements like this. And you're like, man, what's up with that? A sequence Sn is bounded if there are numbers k and m such that the sequence is between those two numbers. That first sentence sums up to, you might have a sequence that exists inside this room, meaning it can go up to the ceiling, it can go down to the floor, but it can't go outside. That's it. So for example, you might have a sequence 1, then 1/2, then 1/3, then 1/4. That would be called a bounded sequence because it's not going greater than 1, and as far as you can tell, it's never going to be less than 0. So it's bounded between 1 and 0. There's some logic in there. It's not that important that you totally understand the logic in the wordy part of that, but the blue box is what's important, that you understand where it comes from. A convergent sequence is bounded. What that means is, if you have some value that you're cruising in on, right? Remember that first question on the test? If you're asymptote, right? You're cruising in on. So this asymptote would be the limit of the terms in this sequence, right? It has to be bounded, meaning there is you can choose a lower bound and an upper bound. Because here's the thing, if it wasn't bounded, could it converge? converge? No, if a sequence is unbounded, can it converge? It's like the opposite of converging, right? All it's saying is if something is converging, it has to be bounded. Okay. Now they choose, truly interesting, you might get hung up on the fact that the terms are bounded by the limit minus 1 and the limit plus 1. Could you choose any values for this right here, like L minus 2 and L plus 2? If something is converging to L, you can choose this, like basically it's like, okay, is the ceiling above me? Yeah. Well, are the birds above me? Yeah. Are the clouds above me? Yeah. Is like the solar, is like the sun above me? Yeah. The point is you can choose it arbitrarily high or close. That's all it's saying. What about bounded sequences though? Do bounded sequences always converge? No. We just saw one, right? 2, 0, 2, 0, 2, 0. Is that bounded? Yeah, it's bounded between 2 and 0, but does it converge? No. Okay, so let's go to kind of the meat of what we're doing here. I just really want to focus on these. I want to cut out those words. Umi doesn't like words, so we'll just look at numbers, okay? Is that good? This is a sequence. Or is it? Is this a sequence? We have crossed over into what? Series. Exactly. We've crossed over into series. So what's the only difference here? What do we now have? We have sums. Exactly. We have sums. That's the only thing that's changed here. Has anybody seen this particular series before? Does anybody know what that's called? There's a special name for that one. Did anybody find out what it is? It's okay if you haven't. I'm just curious if somebody's seen it before. It's okay. That one's pretty cool. The nth term is just 1 over n, right? It's kind of neat. The next one, what type of series is this one? What type of series is this? What type of series is it? You know what type it is. It is geometric. Why is it a geometric series? Why is it a geometric series?
Because each term is multiplied at a ratio.
The same ratio, yeah. So like the different here, 110, 110, 110, right? There is a constant ratio that is a geometric series. What we look at, and what we're really interested in, what happens when you add up a lot of these terms? You've done this before. The first half of your calculus class last year was differentiation. What was the second half of your calculus class? Integration, exactly. It was integration. So you've differentiated, then you've integrated. But when you integrated, how did you initially integrate things? What did you do? You created what? Slices. And then what did you do with those slices? Add them all together. So you had a formula which represented the summation of all these things, and then you took a limit that went to infinity, and that limit approached the actual area under the curve, right? So you've done this before. So we're going to explore it just a little bit to see what kinds of formulas we can come up with, and you might remember some of them from your notes. So let's talk about one of them right here. Yeah, let's talk about this one right here. Let's do this one here. So if I had, let's go to, this question right here. Speak so humans can hear. I can't hear you, okay? 4% of 250. So D2, meaning you put in the second dose, right? But then what's left of the first dose? 250 times what? 0.04. So this right here represents what's left of the first dosage. Are you with me? So when you do dosage 3, you're putting 250 into the system, right? Well, what's left of dosage number 2 here? 250 times 0.04. But what's left of dosage 1? 250 times 0.04 to the... So this right here, I'll just connect these. That's what happens to dosage 1. What about this one? That's dosage 2. So could you keep on writing these out? So theoretically, could we write out 10 lines of this? Sure, we could absolutely write out 10 lines of this. Does that seem like an inefficient or an efficient way of going about doing this problem? Seems decent.
Relative to some things.
That's a very good answer, actually. Everything is relative. So what? Let me take this here. If I can actually get my... Where do you think? There it is. Good. Hello. Oh, you're going to go away, aren't you? That's...
Can you pull up Let's start anything.
Reviver, yeah. Let's start anything. Okay, so you see this right here? You should actually see something in there that we've already seen. So if you do this out, you do Q10 and multiply it by that. What is this right here? It's the Q what? No, you said it right. It is Q10, right? Is everybody with me so far? That is Q10 because look, you had. Yeah. So look what happens here. If you subtract the two, what are you left with? If you subtract these two things, you take this and you subtract that. What happens? What cancels? A lot of terms, right? A whole bunch of terms. If you take this and subtract this, what goes away? That goes away. 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 Leaving you with just what? 250. So if you subtract those two, you're just left with, oh, this is kind of cool. I mean, I think it's pretty cool. You end up with this right here. I think I actually already pasted it in. When you do the subtraction, you end up with this. This thing right here. Now, is that a nice formula to work with? Let's generalize it though. It's nicer, yeah, and relative. Let's generalize it though. What was 250? What? Initial. What was this? The ratio. And this is the ratio again. So do we now really, that all of this math, you can generalize it and get the general formula. They like using x for the ratio. I don't know why. I don't know why they do that. But the idea is, if I give you an initial and a ratio, can you find out what it sums to? Yeah. Now what happens if the ratio is greater than 1? It diverges, yeah. If the ratio is greater than 1, it diverges because anything greater than 1 to the n power when n goes to infinity goes boom. It goes boom. Okay, if you do that, so this is what you generally see. In this case, what is our initial term? Our initial term is a, and what's our ratio? Ratio is x, yeah. So a geometric series has that form, and an infinite geometric series, what's the only difference? One stops and one doesn't. That's it, okay? What's really nice about the formula we have, what do we now have for our sum? Our sum formula is going to be a times 1 minus x to the n all over what? 1 minus x, right? What's really nice about this, does it work in just one of these cases? Does it work in the finite case? Does it work in the infinite case? Does it work in both? Which one or both does it work in? Both, exactly, right. So we like looking at it, and we take the limit as n goes to infinity, maybe it converges, maybe it doesn't, right? But you're still evaluating an infinite series. Or, if it ends, we don't have to calculate each individual piece. We can just plug in a number to get the sum of the first 19 terms. What have we found out about sometimes building these formulas can be challenging? In this case, for geometric series, is it rather straightforward? Yes. Why did I kind of hand wave myself through this work right here? I hand wove my way through it because do I expect you to build that formula every time you want to use it? No. This formula right here, you can just use it whenever you want to use it. You don't have to prove it, okay? You do not have to prove it. But I do really like this maneuver. This is if you got anything out of this class, I love this maneuver because you know that this right here is Q10 right here. Subtracting something from a multiple of itself is a really cool mathematical operation. You will definitely do that in future math classes. It's also kind of weird because it's kind of like pulling things out of thin air. Like before someone saw that, they're like, what the heck do I do to this, right? And then they're like, let's multiply it by 0.04 and see, oh, there it is. You know what I mean? Like just because it's a simple maneuver doesn't mean it was simple to find. Okay, let's keep going. So we now can do that. We can do a infinite and finite. So we have 3 of them right here. 3 of them right here. How about you push all the desks? We could do that. Remember that. First one, is this a geometric series? Yeah, it looks like it. What's our initial value? 1, and what's our, they call it x. I like calling it the r value. What's the ratio? 1/2. So what's the sum going to be? 1 over So it's going to be what? 2. Yay. Nice. What about the next one? You can just look at it and tell me what. What does it do? It diverges. So it keeps on getting bigger. It don't work. What's the ratio? The ratio is definitely greater than 1, right? It's 2. What about the next one, Cade? What's the initial value? What's our ratio? Can the ratio be negative? Is that okay? Yeah, sure. All it means is it dances back and forth. And you know what? When you do out this proof, this math right here, this math that we did right here in this one, it doesn't actually change if the ratio is negative. All those terms still cancel. The formula still holds. So when you do this one out, going back down here, what do you get for your sum? Yeah, not 6, sorry. 6 over what? Sorry. 6 over 1 minus negative 1/3. So that's 6 over 4/3, which is 18 over 4, which is the answer you just told me, which is what, 9 over 2? Yep, good job. Okay, so on this one right here, people who save money often do so by putting some fixed amount aside regularly. To be specific, suppose $1,000 is deposited every year in a savings account earning 5% yearly compounded annually. What is the balance BN in dollars? Now, what did I say about the formula? Are you allowed to use this geometric series formula? Sure. What's our initial value? 1,000. What's the ratio between each term? 0.05. Now, seeing that is a little challenging. Seeing that is a little challenging in this one because the way you write it, usually we would like to write it like this, right? 1,000 plus 1,000 times 1.05 plus 1,000 times 1.05 what? Squared, and so forth, right? But the way this is structured, when you put $1,000 into a bank account and it's there for a total of 10 years, which of these terms is that going to be? Effectively what I'm saying is they're written backwards. Remember how we did it up here? Remember this one right, this one right here? This was our first dosage, right? But where does that term keep on migrating? It keeps on migrating here to the right, so we can write it in descending order. Does that kind of make sense? So the idea is on this one right here, $1,000 compounded for 10 years at 5% interest would be this, correct? In the logic of how this problem is, that would be the first $1,000 that I put into the bank account, right? All I'm saying is, if you were to write this out, when you write it out, it looks like it's backwards. It's not backwards. It's just it is backwards. It's just backwards because we like to write things as the number and then the number times the ratio once and then the number times the ratio twice. Does that kind of make sense? The idea though is, do you need to write that whole string out every single time you want to do a question like this? Shake your head no. You can just use the formula right here. This right here is the ratio. This is your A value, or they call it the X value, right? Should this diverge if n goes to infinity? Yes. If you keep on putting $1,000 into an account every year, are you going to have it better get bigger, or there's something very wrong, okay? Something very wrong. I don't know, there's a global financial crisis and money ceases to exist. I don't know. The point is, you now can use this formula. It's relatively straightforward. Okay, so yeah, I think you want to do some warm-up.